In the previous section, we synchronized Delta Sigma and on-demand C-series modules. By the end of this module, you will be able to describe the basics of using SubVIs in LabVIEW. In Lesson 10, we'll talk about modular programming on the FPGA. So first we'll start off with a quick review of SubVIs in general. Then we'll talk about using SubVIs on FPGA. Then we'll talk about how re-entrancy and non-re-entrancy on your SubVIs work in FPGA. We'll talk about passing FPGA items to SubVIs in FPGA. We'll also talk about how you would test those SubVIs as well. Okay, so let's talk about modularity real quick. So modularity defines the degree to which a program is composed of separate, discrete modules such that a change to one of those modules has minimum impact on other modules. So in LabVIEW, these modules are going to be implemented as SubVIs. So SubVIs we talked about in the LabVIEW Core 1 course and in a lot of LabVIEW Basics courses as well. So in this section, we'll just kind of do a quick review of what SubVIs are. So a SubVI is a VI within another VI. If you're taking a look at a SubVI front panel, you can see that in the upper right-hand corner, you have the icon that's associated with that SubVI, and that's how it'll show up if it's placed in a main VI. And you also have some connector panes as well. So again, the icon that you define for your SubVI, that's how that SubVI will show up if it's placed in a main VI. The connector pane is going to define the inputs and the outputs of that SubVI, and those inputs and outputs that are passed from the main VI into and out of that SubVI. So remember, to set up the connector pane, you want to right-click the connector pane, go to Patterns, and you can select one of those patterns. The default one, and the one that most people use, is the 4x2x2x4 connector pane. With SubVIs, you can also set the terminal setting to either be a required terminal, a recommended terminal, or an optional terminal. The required terminals will show up as bold on the context help, and the recommended ones will show up as just plain font. So to do this, you would open up your SubVI, and then if you go to your connector pane, after you've wired the connector pane up to the corresponding controls and indicators on the SubVI, you can right-click a terminal on the connector pane and select whether you want that terminal to be required, recommended, or optional. So let's say you have a section of your main VI and you take a look at it and you see that it would be better suited as a SubVI. What you can do is you can use your mouse and you can highlight the section that you want to be enclosed inside a SubVI, and then you can select Edit, Create SubVI, and notice how on the slide it will shrink it up into a SubVI. At that point, you probably want to open up that SubVI and give that SubVI a descriptive icon. Now you can describe the basics of using SubVIs in LabVIEW. Next, we will describe the basics of SubVIs, re-entrancy, and non-re-entrancy in LabVIEW FPGA. In the previous section, we described the basics of using SubVIs in LabVIEW. By the end of this module, you will be able to describe the basics of SubVIs, re-entrancy, and non-re-entrancy in LabVIEW FPGA. Now let's talk about using SubVIs on the FPGA. So you can run only one top-level FPGA VI. Okay? However, you can have several SubVIs. So remember before when we were talking about it's bad to put large controls and indicators on a front panel? Well, that only applied for the front panel of a top-level FPGA VI. If you're using a SubVI, on the FPGA SubVI, you can place large controls and indicators on that. And the reason for that, it's because SubVI controls and indicators are not exposed to the host. Only the controls and indicators that are on your top-level FPGA VI are exposed to the host. So now let's talk about re-entrancy and non-re-entrancy in FPGA. So if you're familiar with LabVIEW on Windows Target, when you create a SubVI for Windows, by default, the VI properties is going to show that it is a non-re-entrant SubVI. Now, when you create a new VI in FPGA, by default, it's going to be different. By default, creating a VI on FPGA is going to be re-entrant. So just wanted to point that out to you. One of the reasons why we would do that on FPGA is on FPGA, it's easy to have a lot of things run in parallel. Okay, so that's one of the reasons why the default is set to re-entrant. So let's take a look at a re-entrant FPGA SubVI. So if you're using a re-entrant FPGA SubVI, each instance of that re-entrant FPGA SubVI on the block diagram becomes a separate hardware resource on the FPGA chip. So if we take a look at the block diagram on the left, notice we have a re-entrant SubVI and we have 3 instances of it. If we look at how it's implemented on the FPGA, notice that SubVI is actually implemented 3 different times because we have that SubVI 3 times and they're all re-entrant. Okay? Now let's talk about a non-re-entrant FPGA SubVI. So if it's a non-re-entrant FPGA SubVI, then there's only a single instance that's shared by multiple callers. That means every time someone wants to call that same SubVI, it's going to have to wait for somebody else to finish using it. So each call to the SubVI waits until the previous call ends. So in this case, it's not going to allow parallel execution of that SubVI. So let's take a look at this block diagram. Notice that we have 3 instances of this SubVI, but this is a non-re-entrant SubVI. So if we take a look at the way that it is implemented on the FPGA chip, it's only implemented once. Because there's only one implementation of that, those 3 loops are going to have to share that one implementation. So if the top loop is using that non-re-entrant SubVI, the bottom 2 loops have to wait until the first loop is done with it before they can access it. So now let's take a look at the trade-offs between re-entrancy and non-re-entrancy for FPGA VIs. Okay? So first let's talk about FPGA resources. So with a re-entrant SubVI, there's a separate one that's implemented in the FPGA for each instantiation of it on your block diagram. So typically that's going to use up more space on the FPGA. Now let's look at the non-re-entrant SubVI. There's a single implementation on the FPGA chip for all instantiations. So typically it's going to use up less resources. Now let's take a look at parallel execution. If you have a re-entrant SubVI, all those SubVIs, because they're implemented multiple times on the FPGA chip, they're going to be running truly parallel. For a non-re-entrant SubVI, because there's only one implementation of it on the FPGA chip, it won't be able to run in parallel. So if we were to generalize, a re-entrant SubVI will be optimized more for speed because of that parallel execution, and a non-re-entrant SubVI is typically more optimized for size. Now let's take a look at use in a single cycle time loop. A re-entrant SubVI will be able to work in a single cycle time loop because there is a separate implementation of that on the FPGA chip for that re-entrant SubVI. However, if you have a non-re-entrant SubVI, it might not work in a single cycle time loop. The only way a non-re-entrant SubVI will work inside a single cycle time loop if it is only called from one place. That way we know that it will never have to wait for another loop to finish using that non-re-entrant SubVI. Because in a single cycle time loop, it has to execute within one clock cycle. So we can't have a SubVI in there that needs to wait on another loop to finish using that SubVI. Now you can describe the basics of SubVIs, re-entrancy, and non-re-entrancy in LabVIEW FPGA. Next, we will pass FPGA items to SubVIs. In the previous section, we described the basics of SubVIs, re-entrancy, and non-re-entrancy in LabVIEW FPGA. By the end of this module, you will be able to pass FPGA items to SubVIs. So in this section, we're going to talk about the different ways that you can pass FPGA items to SubVIs. So for example, you can use FPGA I/O controls in SubVIs. You can pass FPGA clocks. You can pass memory items, register items, and FIFO items into SubVIs. Now, what's the advantage of doing this? Well, if you had some code that you were doing on some I/O, for example, and you wrote it and you wanted to reuse that code for several different ports or 7 different lines or channels, you can reuse that as a SubVI, and it makes your code very readable and a lot easier for you as a developer. So one of the keys of using SubVIs is having reusable code. So let's talk about the FPGA I/O control. With an FPGA I/O control, what you can do is you can use a control to specify the FPGA I/O channel. So if we take a look at this particular example, let's take a look at the block diagram on the right. Okay, so this is the code that is existing in our SubVI. So notice that we have a DIO port. Okay, and that's a control where someone can select what digital I/O port they want to use, and that reference is passed into a FPGA I/O node. Okay, so at that point, this SubVI is able to do some sort of logic on a digital I/O port that is specified by a control. Okay, so now let's take a look at the block diagram on the left. So this is the main VI. Notice that we have a SubVI with some functionality defined that acts on a digital port, and we have it 5 different times. So now we're able to reuse that code and use it with a digital port 0, digital port 1, digital port 2, digital port 3, and digital port 4. So this is also a SubVI, so we can assume that it is sticking with the default setting of re-entrant. So notice that all 5 of these things are happening at the same time for 5 different ports. So this is a nice reusable code and a great use case for using SubVIs. So let's take a look at this in LabVIEW and see how we can do this. Okay, so let's take a look at this particular project. Okay, so in this project we have 4 different ports, and we do want to use the same logic on all 4 of those ports. So let's go ahead and look at this particular VI that we have. Okay, so if we look at the block diagram, notice that we've created this particular block diagram kind of in the old method before we knew about SubVIs and FPGA controls. Okay, so if we take a look at this, what we're doing is we've specified and we've hard-coded this I/O node to work only with digital port 0. Okay, so we're going to write some data to digital port 0. We're going to wait for some time, and then we're going to also use a method of digital port 0, and we're going to now read from digital port 0. Okay, so in this case, all this code is hard-coded. If I wanted to do this with 4 different ports, then I would have to write 4 separate pieces of code that are hard-coded with port 0, 1, 2, and 3. Okay. However, if I make this into a SubVI, that would be a way that I can reuse this code. Okay. So how would we do this? If we had this VI, notice that the FPGA I/O node, there is this input here that we can create a control from. So this is a reference. I'm going to right-click this. I'm going to go to Create Control. Okay, so notice now that this particular I/O node, the digital port that's associated with it is determined by this control up here. So if I look at this control up here, notice that I can go in here and now I can get digital port 0, 1, 2, or 3. Okay, so let me go ahead and update this SubVI. And what I'm going to do is I'm going to take that reference and I'm going to pass it into my other function. So now notice that this is the digital port that this is associated with is determined by this wire. And I'm going to go ahead and pass it into this node as well. Okay, so all 3 of these FPGA I/O nodes are all associated with whatever's coming in on this control. Okay, and if I wanted to make this into a SubVI, what I could do is I can go ahead and wire this up. So now from the main VI, now that I've used the connector pane, I can actually pass in digital port 0. Okay, and let's say I wire the rest of these up. Okay, and I'm going to save this, and now I'm going to create a new VI. So if this was my main VI, what I'm going to do is I'm going to do a quick shortcut here and drag it over here. So now I've got my SubVI, which I didn't do a connector pane of, but I just wanted to show you real quick that the SubVI would show up like this on my main VI, and notice that I've got a terminal there. I can create a constant, for example, and now I can say digital port 0, and what I can do is I can actually make copies of this SubVI, and now I can set this to digital port 1, digital port 2, and digital port 3, and now I've been able to very easily reuse my code for different ports. Okay, so on this slide, we see how to create an FPGA I/O control, which I just demoed. So basically, you would place a FPGA I/O node in a SubVI. You would right-click the FPGA I/O input and select Create Control. And then you would wire the FPGA I/O control to the SubVI connector pane. That way, your main VI can actually access that control. Okay. So typically, what you want to do is you want to place down the FPGA I/O node that you want. So for example, if it's a digital port, or if it's analog in or analog output, and then if you right click and create the control from that particular FPGA I/O node that's already configured, then that control will automatically be able to be configured for whatever data type that you wanted. For example, analog input or digital port. So another type of FPGA control that you can pass into SubVIs is a FPGA clock control. So on this example, we see we've created a SubVI, and inside the SubVI there is a single cycle time loop with some code in there. Okay, and what we've done here in the SubVI is we've created a control by right-clicking the input of that single cycle time loop and creating control. We've made a clock control. So that way on our main VI on the left, we're able to execute that code, which is actually just doing a pulse train, and we're able to feed it in different FPGA clocks. So now on that main VI, by using that SubVI, we've created a pulse train that's running at 40 megahertz, another pulse train that's running at 80 megahertz, and another one that's running at 120 megahertz. Okay, so this is a nice way that you can use FPGA clocks to control the different rates of a SubVI. So the way that you would create a FPGA clock control is you would place a single cycle time loop in a SubVI, right-click that source name input, and select Create Control. At that point, make sure that you wire the clock control to the SubVI connector pane so the main VI can access it. So in the same way, you can do the same thing with FPGA memory items, register items, and FIFO items. Okay, so if you want to create a SubVI that works with any of those items, create the SubVI, place the memory item, register item, or FIFO item in there, and then again, you're going to right-click that input and create a control for it. Make sure you wire that control to your SubVI connector pane, and now your main VI can access it. So this is a great way of creating reusable code and putting them in SubVIs. Okay, so real quick, just wanted to go over some FPGA control restrictions. Okay, let's go over the first one. You cannot change the value of FPGA controls and indicators while an FPGA VI runs on the development computer or when using interactive front panel communication. So basically, you can only change the value of an FPGA control on the front panel when the VI is not running. This is because FPGA control ref nums must be constant references during runtime. Another caveat, so you cannot access FPGA controls and indicators from the FPGA interface. So we haven't talked about the FPGA interface quite yet. That's something that's going to be on your host VI. So for now, the thing I want you to take out of this is you're not going to be able to access the values and change the values of the FPGA controls and indicators that we talked about in this section from a host VI that's running on RT or Windows. Lastly, you can bundle FPGA name controls into clusters with other FPGA name controls with occurrence ref nums and with other data types. However, you cannot have this kind of a cluster on the front panel of your top level FPGA VI. LabVIEW will return an error when you attempt to compile that FPGA VI. So this is okay in SubVIs, but not on your top level of FPGA VI. Now you can pass FPGA items to SubVIs. Next, we will test FPGA SubVIs. In the previous section, we passed FPGA items to SubVIs. By the end of this module, you will be able to test FPGA SubVIs. When you're testing FPGA SubVIs, you can test them as if they were top-level VIs. So for example, once I've created a SubVI, what I can do is I can execute it on the development computer and make sure all the functionality is correct. And then after that, if it makes sense to, I can also execute that SubVI on an FPGA target to make sure it works on the FPGA. After I've confirmed that, I can go ahead and put my SubVI into my calling VI, and then I can test that calling VI on the development computer just to make sure everything's working there. And then after that, I can also execute that whole thing on the FPGA target. Okay, so now if you have time, go ahead and do exercise 10.1, and here we'll create an FPGA SubVI, and then we'll put it into a main VI, and then we can do some testing on it as well. So for now, I'm going to open up the solution and go through it with you. Okay, so let's take a look at the exercise 10.1 solution. So in this exercise, you're going to build a SubVI, and you're going to use it on a main VI. And the SubVI is going to use some FPGA I/O as well. So let's open this up. Notice we have an analog input FPGA I/O node, also a digital output I/O node, and both of these are going to be accessible from our main VI. Okay, we have a AI scan period, a threshold, and we're going to see what the AI value is, and we're going to see if that threshold was reached. So let's take a look at the block diagram. So in the block diagram, notice that we've got some reusable code. We have a loop timer here, so there's no while loop here. The reason why is because in this application, we're going to put the while loop in the main VI, the top level VI. Okay, so here we have a loop timer. We're going to be able to tell it what loop rate to run at. So that's our AI scan period. And then we're going to take a look at the analog input. We're going to extract the I/O from that. We're going to compare it and get the see whether the threshold was reached yet. We're going to output whether the threshold was reached to an indicator, and we're also going to output that result to a digital output, which is specified by this FPGA I/O control. Okay. So because we have this as a SubVI, we can reuse it, and we can reuse it with several different digital output and analog input channels. So let me close this. The other thing I want to show you real quick is if we look at the VI properties, we'll see that this SubVI kept the default setting for re-entrancy. So if we go to VI properties and go to the execution category, so notice that we're going to the execution category here. Notice that re-entrancy is on. Okay, so if I wanted to make this non-reentrant for some reason, then I can click on the non-reentrant execution item here. But I'm going to leave it in this case as reentrant because I do want it to be able to run in parallel with other instances of the SubVI. So I'm going to just cancel out of here. Now let's go ahead and close this. And let's go to our main VI. Actually, before we do that, let's go ahead and open up our SubVI again. Notice that right now I've got my FPGA target here, and it's going to be executing on a dev computer. Okay, so I can go ahead and run this. I probably won't be able to test out the scan period really well, but I can test the threshold and the AI. So let's see if this logic works. So it looks like our output that we got, our simulated I/O from our analog input channel was 29361, which is greater than 0. So threshold reached is going to be true. Okay, let me run it one more time. And if you're creating a SubVI, you can run it a couple times and make sure that in the simulated environment everything's working okay. So look, we have a threshold of 0. We have something that is below 0, negative 16471, and threshold reached is off. Okay, so for that quick test, it looks like everything's working all right. So I'm going to go ahead and close this. So now let's go to our main VI. So notice we've got that SubVI here several times, and because it's reentrant, it'll be executing in parallel on the hardware. Okay, so notice that I've created an analog input channel 0 and digital output channel 0, and then here we've got channel 1 for each of them and channel 2 for each of them. So each of them will be running at their own scan period. Each one of them is going to have its separate maximum limit or threshold. And then we're going to have these indicators for each one indicating the analog input value and whether it reached the threshold or not. Okay, and we have a false going here, so all 3 loops are going to be running indefinitely. So before we do any compiling, of course we want to make sure everything is working in our simulated environment, right? Because here we have our debugging tools and all that. So let's go ahead and run this. So I'm going to put a scan period here. Notice that it's in microseconds. I'm going to make this 1 second. Okay, and I'm going to put a maximum limit of 0. So in this case, because this is an I-16, it's going to go from about negative 32,000 all the way up to positive 32,000 something. So here I'm going to make this one 2 seconds, and I'm going to make this one 3 seconds. And I'm going to make the maximum limit 0 here and the maximum limit here. So in this simulation, about half the time it'll cross the threshold. So let's go ahead and run this. So notice that each of these are updating at different rates. Okay, this one is updating every second, this one is updating every 2 seconds, and this one is updating every 3 seconds. And notice that when this value is positive, that's going to go true. Okay, so again, now that we've verified everything is working in our simulation environment, I can go ahead and stop this. And then at this point, I can go ahead and if I had my FPGA hardware installed, I could right-click, go to here, execute VI on FPGA target, and then I could run this and compile it and test it on our actual hardware. Okay, let's go through the discussion questions now. So the first one, if you needed to monitor additional analog input channels and control additional DIO lines, how would you change your code? So remember, in this exercise, we already have that logic nicely encapsulated inside a SubVI. So in this case, we can reuse that code very easily. We can just drop down another while loop and put the SubVI in there and then wire up its inputs and controls. Okay, let's do the second question now. How would the behavior of this application change if you change the SubVI from re-entrant to non-re-entrant? Well, in this case, right now it's re-entrant, so everything is going to happen in parallel on the hardware. If we were to change that to non-re-entrant, that would no longer be the case. If it was non-re-entrant, then each call to that SubVI would have to wait until the previous call to that SubVI has ended instead of executing in parallel. Now you can test FPGA SubVIs. Next, we will describe the purpose of a host VI and the basics of creating a host VI.